Hey guys, how you doing? It's Coach Scott. Our last video in stoichiometry. Of course, we'll be playing with this for the rest of the year. You know that. So let's get right into it. We're going to be talking about a couple of things: theoretical yield, actual yield, percent yield, and how do we calculate the excess reactant, which is similar to the limiting reactant that we have already talked about. Okay, so hold on to your seats. Here we go. If I can get it to switch over, and there we go. All right, so theoretical yield, here's just definitions. Theoretical yield is the amount of product that could form during a reaction. It's the ones that we calculate. We can call it calculated yields too. And it's calculated from the balanced reaction, and it represents the maximum amount of product that we could form from a given amount of the reactant. Actual yield is what we actually make, right? Which is often, really it is, totally different than what we want to make or what we calculate that we should be able to make. That's the one that you actually made, all right? And we measure it in the lab, we measure it in the factory. And why is actual yield different from the percent yield? Well, let's see. The percent yield is the ratio of the actual yield to the theoretical yield, all right, expressed as a percent. And what it does, it measures the efficiency of the reaction and of the process as you're trying to make stuff, right? So, it's pretty simple. Theoretical yield you calculate, all right, and of course it's limited by the amount of limiting reactant that's in the vessel or in the reaction area. Your percent yield is the ratio of the actual amount produced to the theoretical amount that you should have produced. So it's actual divided by theoretical times 100. Not hard. Here's an example. Find the theoretical yield in grams of aluminum chloride if 27 grams of aluminum and 71 grams of chlorine react. And there's my balanced reaction. 2 moles of aluminum plus 3 moles of chlorine gas yields 2 moles of aluminum chloride. First of all, we got to determine what the limiting reactant is. We'll use the method that we talked about in the last video. So I've got to convert to moles first. 27 grams of aluminum times, well, it has a mass for the periodic table of 27 grams, so I have 1 mole of aluminum. 71 grams of chlorine gas times 1 over 71, that's 1 mole of chlorine. Okay, cool. So I divide these moles by the stoichiometric coefficient, 2 for aluminum, so 0.5 moles of aluminum available. And 1 mole divided by 3, so I have 0.33 moles of chlorine available. Well, that's less than 0.5, so chlorine is the limiting reactant. So I'm going to use the initial amount of chlorine to calculate how much should be produced. Okay? So I've got 1 mole of chlorine gas, got that from right there, times the mole ratio, 2 over 3. So for every 3 moles of chlorine, it's going to produce 2 moles of aluminum chloride, times the molar mass of aluminum chloride, 133 grams, and that's going to give me the theoretical yield in grams of 87.8 grams. See how I do the math. All right, so that's the theoretical yield. Now, if we actually make it and we don't produce 87.8, then we're going to calculate the percent yield. And this is determines the efficiency of the reaction, okay, and it's just a ratio of the actual over the theoretical. So, if I've got a percent yield of 85%, that shows that that's a better reaction or a better produced reaction than if I had a percent yield of 55%. So it's just really a metric we use to compare how good we're doing something. That's really what it is. So it's the ratio comparing the amount actually obtained divided by the calculated. All right, so an example. A student burns 24 grams of methane with 30 liters of oxygen gas in the laboratory. I'll get my pen going. And produces 12.1 liters of carbon dioxide gas at STP. So we've got to determine what is the percent yield. That's what they asked us. So let's see how they did it. I have to use my pen. Good. So first we've got to find the limiting reactant. So I've got to convert it into moles. I do 24 grams of methane divided by the molar mass, 16 grams. It gives me 1.5 moles of methane. 30 liters of oxygen divided by the molar volume, 22.4, means I have 1.33 moles of oxygen. Okay, I divide through by the stoichiometric ratio, our stoichiometric coefficient, 1 for methane, so that's 1.5 moles of methane available. 1.33 divided by 2, it gives me 0.67 moles of oxygen. So that tells me I have less moles of oxygen available. Oxygen is the limiting reactant. So let's find the theoretical yield. So we're going to use the amount of oxygen because that's going to be the max of what I can produce. So I use oxygen, 1.33 moles, times the stoichiometric ratio, 1 mole of CO2 divided by 2 moles of oxygen, times, they gave me liters, so times the molar volume, 22.4, means I should have produced 15 liters of CO2. I didn't. I produced 12.1 liters of CO2. Something went up. So 12.1 divided by 15 gives me, times 100, gives me 80.7. So that is my percent yield. Not great, is what it is. So what is the theoretical yield of phosphorus pentachloride if 2 grams of phosphorus trichloride reacts with 1.5 moles of chlorine gas at STP? So we got to determine our moles. All right, so we're looking at phosphorus trichloride. So let's go first 2 grams of PCl3. Let's convert that into moles. Phosphorus has a mass of 30.974 plus 3 times 16. That has a molar mass of 78.974 grams PCl3. 1 mole PCl3. 2 divided by 78.974 gives me 0.0253 moles PCl3. Okay, so I've got 1 mole, 1.5 moles of chlorine, and I notice that's a 1-to-1 ratio. So PCl3 is less than 1.5, so that's going to limit the reaction. So we'll use that to get the theoretical yield. So 0.0253 moles of PCl3. They're asking for the theoretical yield of phosphorus pentachloride. So I have to use the molar mass. That's a 1 mole of PCl3. 1 mole PCl5 equals moles. They're asking for grams, so I have to convert it into grams. 1 mole PCl5. PCl5 has a mass of, well, let's see, 30.974 times, or plus, rather 5 times 16 equals 110.974. So let's do our math. Times 0.0253. I got, well, about 2.8, so I'm going to say 3 grams of PCl3. That should be the ratio, or the theoretical yield. And it is. Yay. So let's move on to something, and this will conclude this unit actually. How do we calculate the excess reactant? Very similar to the limiting reactant. All right. So we're always going to have some left over, right? if we don't consume both of them. There's always going to be a little bit of stuff left over. This is how we determine how much of that stuff left over is left over. So first, we're going to use the limiting reactant to determine how much of the excess reactant that was required to react. Then we subtract the amount of the excess reactant that was used from what we started with of the excess reactant. Sounds confusing. It's not. So if 6 grams of hydrogen gas react with 160 grams of oxygen gas, how much of the excess reactant remains? So first, find out which one is the limiting reactant. So I'll take my masses and I convert them into moles. 6 divided by 2 gives me 3 moles of hydrogen gas. 160 divided by 32 gives me 5 moles of oxygen. Then we divide by the stoichiometric coefficient. 3 divided by 2 is 1.5. 5 divided by 1 is 5. So hydrogen limits the reaction. All right, so now we have to find how much oxygen, the excess reaction, is required. So we start with the amount of hydrogen we have first. 3 moles of hydrogen gas times the molar ratio means 1.5 moles of oxygen is required for that reaction. So now we subtract it from the initial. Initially I had 5 moles of oxygen. I only used 1.5 moles of oxygen, so I have 3.5 moles in excess. Okay? We didn't use it all. So, for the reaction below, which is the excess reactant if 25 grams of silicon dioxide react with 10 grams of carbon? So always check for balancing. This is balanced because I told you I'm going to balance your reactions until we get to cover balancing reactions. So if I look at this, I have 1 mole of SiO2 plus 2 moles of carbon yields 1 mole of silicon carbide plus 1 mole of carbon dioxide. Okay, so how do we do this? Well, it's A. Silicon dioxide, because we convert that into moles, right? Then divide by the coefficient, stoichiometric coefficient, and then whichever one is left. Let me work it because, well, that's just confusing, that answer. So let's do it. Let me get my pen out. So for the reaction below, I have 25 grams of silicon dioxide, SiO2 times, let's see, 32 times silicons, 28.086 plus 28 has a molar mass of 60.068, 86 rather, 1 mole SiO2 gives me 25, 60.086, 0.416 moles of SiO2. And then I have 10 grams of carbon. 10 grams of carbon, that's carbon. 1 mole of carbon is 12 grams. That's going to give me 10 divided by 12. That gives me starting moles of 0.8333. Then divide by the coefficients. That's 1 divided by 2. Whoop, wrong. 0. Whoops. About 2. That gives me 0.41666. That's SiO2. Well, SiO2 is 0.416, right? And That's 0.41667. Let's try this again. 25 divided by 60.0. 0.4160. All right, so this is going to limit the reaction. All right, so it is A. And that's how they did it. Okay, so that's how you determine excess reactant, how much is left over. So that's our stoichiometry. It's not too bad, and we'll have lots of practice on it as we go into chemical reactions, as we go into gases, as we go into equilibrium and kinetics. So again, buckle up, guys. We're getting there. This is Coach Scott saying toodles and have a great day.